Welcome again to the channel. We continue discussing the problems provided at 2021 American Mathematics Competition AMC-12B, organized for high school students by the organization named American Mathematics Competition, related to Mathematical Association of America. The competition took place at 10th of February 2021. The problems and solutions are available from the site Art of Problem Solving AOPS. The link to it will be placed under the video. All the solutions presented here are checked with the answer key, also available from AOPS site. Solutions from the site were also helpful sometimes. Here you have problems 11 to 14 and 16. Problem 15 comes with a drawing, so it doesn't fit on the page. This problem will be given later in the video along with problem 17. Please don't forget to pause the video and try to solve yourself before proceeding. Problem 11. Triangle ABC has the length of AB equals 13, the length of BC equals 14, and the length of AC equals 15. Let P be the point on AC such that the length of PC is 10. There are exactly 2 points D and E on line BP such that quadrilaterals ABCD and ABCE are trapezoids. What is the distance DE? Let's first observe that the length of segment AP equals the length of segment AC minus the length of segment PC. This is 5, which is exactly half of the length of PC. So we can write that the length of PC is twice the length of AP, which will be even more helpful than the lengths themselves. Next, we need to find points D and E completing triangle ABC to trapezia, while line BP is claimed to have exactly 2 such points. Indeed, line BP contains point B, which leaves vertex B out of question. The remaining vertices of the triangle ABC are A and C. Through each of those vertices, we draw a line parallel to the opposite side of the triangle, and the intersection points with the line BP are the ones we are after. Since we need just the length of segment DE, the order of naming points doesn't matter. For certainty, let D be the point on the line drawn through vertex A, and E be another point. So we can write that BC is parallel to AD, and AB is parallel to EC. Consider triangles APD and BPC. They have 2 pairs of alternate interior angles formed by parallel lines BC and AD. Angle PAD equals angle PCB, and angle PDA equals angle PBC. Therefore, triangle APD is similar to triangle BPC by angle-angle rule, and we can equate the ratios of sides. PD to BP equals AP to PC. As we've already seen, PC is 2 times longer than AP. Therefore, the ratio AP to PC and PD to BP as well is 1 to 2. So we can write that the length of PD is half the length of BP. Now consider triangles EPC and ABP. Again, we have 2 pairs of alternate interior angles, this time formed by parallel lines AB and EC. Angle PC equals angle PAB, and angle PEC equals angle PBA. So, triangles EPC and ABP are similar to each other, and again we can equate the ratios of corresponding sides. This time the ratio goes in the opposite order, PC to AP. So its value is 2 to 1. And we write that the length of PE is 2 times the length of BP. Now we can write the expression for the length of segment DE. The length of DE equals the length of PE minus the length of PD. Substituting the lengths of segments PE and PD, we find that the length of segment DE is 3/2 the length of segment BP. So the only thing we need to be completely happy is the length of segment BP. So let's clean up some space, write down that the length of DE is 3/2 the length of BP, and concentrate on finding the length of BP. Cosine rule seems to be the way. So we apply cosine rule to the side BP of triangle ABP. This gives equality 11.1. In the right hand side of the equality, everything is known apart from cosine of A. Can we find cosine of A? Of course we can, from triangle ABC. Again we apply cosine rule, this time to side BC in triangle ABC. And we get equality 11.2. Let's compare the last two equalities. Equality 11.1 contains AP in two places. Equality 11.2 contains AC instead. But AC is AP plus PC, while the length of PC is twice the length of AP. This means that AC is 3 times longer than AP. Therefore, in 11.2, the length of AC can be replaced by 3 times the length of AP. This gives equality 11.3, which looks much more convenient than its predecessor. We are going to eliminate cosine of A contained in the last terms of equalities 11.1 and 11.3. We see that these terms differ only in factors 2 versus 6. So we first multiply 11.1 by 3 and get 11.4, then subtract 11.3 from 11.4. This gives a rather simple equation from where we can find the expression for BP squared. Substituting the values, we get BP squared equals 128. Therefore, BP is 8 times square root of 2, and DE, which is 3/2 of BP, equals 12 times square root of 2. Choice D. Using the cosine rule often leads to tedious computations, but this time it was nice and easy. How about the next problem? Problem 12. Suppose that S is the finite set of positive integers. If the greatest integer in S is removed from S, then the average value arithmetic mean of the integers remaining is 32. If the least integer in S is also removed, then the average value of the integers remaining is 35. If the greatest integer is then returned to the set, the average value of the integers rises to 40. The greatest integer in the original set S is 72 greater than the least integer in S. What is the average value of all the integers in set S? So, L is the least, the smallest integer in S. G is the greatest, the biggest integer in S. P is the set of other integers from S. N is the number of elements in P. Q is the sum of elements in P. Using this notation, set S can be represented as the union of single element sets containing L and G and set P. Therefore, the sum of all elements in S is L plus G plus Q, while the number of elements in S is N plus 2. Consequently, the average value of the elements in S is L plus G plus Q divided by N plus 2. And this is the value we need to find. Now let's follow the condition of the problem step by step. Element G is removed from S. The remaining set is set P with the addition of element L. This means that the sum of remaining elements is L plus Q, while the number of remaining elements is N plus 1. Therefore, the average value of elements is now L plus Q divided by n plus 1, and according to the conditions, this value is 32. This gives equation 12.1. L plus Q equals 32 times n plus 1. Now element L is also removed, so we are left with just set P. In this case, the sum of elements is just Q, and the number of elements is n. So the average is Q divided by n, and this average is equal to 35. And we write equation 12.2. Q equals 35n. Element G is returned to the set. Now the set consists of P with added element G. Sum of elements is G plus Q. Number of elements is n plus 1. The average is G plus Q divided by n plus 1, and it is 40. And we get another equation. Equation 12.3. G plus Q equals 40 times n plus 1. And there is another condition that the greatest integer is 72 greater than the least integer. This gives equation 12.4. G minus L equals 72. Too many equations, you may think. Not at all. Let's subtract 12.1 from 12.3. We get G minus L equals 8 times n plus 1. But according to 12.4, G minus L is just 72. So we get 8 times n plus 1 is 72, and n is 8. Now we know the denominator for AS, and the only thing remains to find is the numerator, L plus G plus Q. To do that, we add equation 12.1 and 12.3 and subtract equation 12.2. In the left hand side we get L plus G plus Q, which is just what we need, and the right hand side can be computed as we know the value of n. Normally we would match similar terms in the right hand side, but here we just substitute the value of n, and since 8 is a divisor of 72, it can be factored out. So we get 8 times 46 for the numerator of AS, and we can find AS. Since the choices are given as decimal fractions, denominator 10 is perfect here. So we don't reduce the fraction and just get 368 tenths or 36.8. Choice D. That wasn't too hard and entertaining as well. And in a great mood, we proceed to problem number 13. How many values of theta in the interval from 0 to 2 pi, excluding the n's, satisfy the equation 1 minus 3 times sine of theta plus 5 times cosine of 3 theta equals 0? To me, the problem looks really consistent with its number since I hate counting. After all, I am not a computer, but a computer programmer who enjoys solving math problems, while the counting problems simply don't move me. What is really peculiar, most of people identify mathematics with counting. What an awful delusion. I would expect to see much more math enthusiasts if the subject were presented not as a computational tool, but as an intellectual challenge. But back to the problem, which actually has a positive feature. It doesn't ask for the actual solutions, it only asks to count them. In fact, I doubt that the precise solutions can be found. There is a formula for cosine 3 theta, but if we apply it, we get an equation containing both sine and cosine of theta with different factors. This makes it really hard, if possible, to solve. So let's abandon this idea and consider graphic solution, which is just right for counting. 5 times cosine of 3 theta is the troublemaker here, so let's penalize it by placing a side. This splits the equation into two functions. f of x equals 5 times cosine of 3x corresponding to the left-hand side of the equation, and g of x equals 3 sine of x minus 1, corresponding to the right-hand side. So we need to plot the graphs for both functions and count common points. Let's start with function f of x. Its graph is obtained from the graph of function y equals cosine of x by squeezing 3 times along x-axis and expanding 5 times along y-axis. This results in changing the aspect ratio using video terminology. However, the maxima and minima will be still exactly in the middle, between 0 points, and they follow in alternating order, maximum after minimum and minimum after maximum. This suggests that we only need to find the 0 points and the values of f of x for the endpoints 0 and 2 pi. This will also give our maxima and minima. So we write that the least positive period is 2/3 of pi, but 2 pi is also a period. Therefore, f of 2 pi equals f of 0, which is 5. And we've got the values at endpoints. Let's also write that the maximum value of f is 5 and the minimum value of f is -5. To find zeros, we need to solve the equation cosine of 3x equals 0. We get 3x equals half pi plus pk, where k is an integer, and x equals 1/6 of a pi plus 1/3 of pi k, where k is an integer. Therefore, the distance between two consecutive zeros is 1/3 of a pi. We are only interested in the values of x in the interval from 0 to 2 pi. This gives an inequation for k, from which we find that k is between 0 and 5, including the ends. This means that we have 6 points in the interval, starting from x equals 1/6 of pi, corresponding to k equals 0, and any next value is obtained just by adding 1/3 of pi. So we can write down all 6 0 points and plot them on the coordinate plane. Then we know that the maxima and minima have y coordinates 5 and -5 respectively. The function has value 5 at both endpoints, therefore 0 and 2 pi are the maximum points. The other maxima and minima alternate and have x coordinates just in the middle between adjacent 0 points. Now we can plot the graph for function f of x in the interval from 0 to 2 pi. And we move to function g of x. The graph of g of x is obtained from the graph of function y equals sine of x by expanding 3 times along y-axis and then shifting down by 1. No scaling along x-axis is involved, therefore the least positive period remains 2 pi. At the endpoints 0 and 2 pi, sine of x equals 0. Due to the presence of free term -1, g of 2 pi equals g of 0 equals -1. Sine of x also becomes 0 just in the middle of the interval for x equals pi, so g of pi is also -1. And we can plot these 3 points on the coordinate plane. Finding zeros for g of x doesn't make sense, as it ends up with arcsine of 1/3, the exact value of which is unknown. However, we can find maxima and minima for g of x. The maximum value of g of x is reached when sine of x equals 1. There is only one corresponding value of x in the interval, x equals half of pi, and the value of g is 2. The minimum value of g of x is reached when sine of x is -1. And again there is only one corresponding value of x in the interval, x equals 3/2 of pi. The minimum value of g is -4. So we plot the points corresponding to maximum and minimum of g. Then we plot the graph of g of x in the interval from 0 to 2 pi. The only thing remained is counting common points of the graphs by gliding along the graph of function g of x. So let's do it. 1, 2, 3, 4, 5, 6. That's choice D. And we leave problem 13 for problem 14. Let ABCD be a rectangle and let DM be a segment perpendicular to the plane ABCD. Suppose that DM has an integer length and the lengths of segments MA, MC, and MB are consecutive odd positive integers in this order. What is the volume of pyramid MABCD? So we have a rectangle ABCD which I've drawn a bit tilted since this is going to be a 3D drawing. MD is perpendicular to the plane containing rectangle ABCD, and the length of segment MD is a positive integer m. The lengths of segments MA, MC, and MB are consecutive odd positive integers. This means that the lengths form an arithmetic progression with common difference 2, where the length of MC is the middle element of it. So let n be the length of MC, then the lengths of MA and MB are n-2 and n+2 respectively. Here n is an odd number which must be no less than 3, since the length of MA is also positive. So we write that n is 2n prime plus 1, where n prime is also a positive integer. All that was just paraphrasing the conditions. So let's step ahead and draw diagonal BD. Since ABCD is a rectangle, triangle ABD is a right-angled triangle with hypotenuse BD. So we can write that BD squared equals AD squared plus AB squared. But a rectangle is also a parallelogram, so side AB is equal to its opposite side, CD. Therefore, the last equation can be rewritten as BD squared equals AD squared plus CD squared, equation 14.1. Since MD is perpendicular to the plane ABCD, it is perpendicular to any line in this plane. In particular, MD is perpendicular to DA, DC, and DB. This means that triangles MDA, MDC, and MDB are right-angled triangles, while MA, MC, and MB are the hypotenuses of these triangles respectively. So we can apply Pythagoras theorem to the triangles. From where we can get expressions for sides AD and CD and the diagonal BD of rectangle ABCD. Here we replace the length of MD with m and substitute the values for lengths MA, MC, and MB in terms of n. This gives the expressions for the lengths of AD, CD, and BD in terms of m and n. And we substitute the expressions into the equation 14.1. This gives an equation for m and n, where we reduce similar terms and get equation 14.2. So the geometric problem has turned into an algebraic problem. Now we need to solve the equation 14.2. Let's complete first two terms to the full square by adding 16 to both parts of the equation. Now the left-hand side can be represented as the difference of two squares. This is equation 14.3. Remember that n is an odd number. Therefore, n-4 and n-4 squared are odd numbers. 16 is an even number. Therefore, m squared must be an odd number, and so is m. Since m can be equal to 1, we write that m equals 2m prime minus 1, where m prime is a positive integer. Now we substitute the expressions for m and n in terms of m prime and m prime into the equation 14.3. And we factorize the left-hand side. We see that both factors in the left-hand side are divisible by 2. Therefore, we can simplify the equation by dividing both its parts by 4. Thus, we get to the equation 14.4. Note that the second factor in 14.4 is a non-negative number, and it cannot be 0 either, because that would turn the left-hand side into 0 and make it different from the right-hand side. Therefore, the second factor must be positive. Then the first factor must be also positive, as the product is a positive number. Now take the difference between the second and first factors. The result is a positive odd integer. Therefore, the second factor must be more than the first factor, and they should have different parities. There is only one way to represent 4 as a product of two distinct positive integers. 4 equals 1 times 4. The factors have different parities, which is great. So we write the system of simultaneous equations by equating the factors to 1 and 4 respectively, simplify it, and get the solution. N prime equals 4 and m prime equals 2. Now we can find the values of n and m. N equals 9, m equals 3. Therefore, the length of the perpendicular segment dm is 3. The lengths of sides MA and MC are 7 and 9 respectively. Back to geometry. We need to find the volume of pyramid MABCD, denoted with letter V. This volume is equal to 1/3 the area of the base, which is rectangle ABCD, times the height of the pyramid. Since dm is perpendicular to the plane ABCD, dm is the altitude of the pyramid. Therefore, the height of the pyramid is the length of dm, while the area of the rectangle ABCD is of course the product of its sides AD and CD. So we get that V is 1/3 the product of the lengths of AD, CD, and DM. The length of DM is known. The lengths of AD and CD are found from already familiar to us right-angled triangles, MDA and MDC. The only remaining thing is substituting values into the formula for the volume. We get 12 times square root of 20, which is not in the choices. However, this is easy fixable as square root of 20 is 2 times square root of 5. Finally, the volume is 24 times square root of 5, choice A. So far so good, and we proceed to problem 16. Let g of x be a polynomial with leading coefficient 1 whose 3 roots are reciprocals of the 3 roots of f of x equals x cubed plus ax squared plus bx plus c, where 1 is less than a, less than b, less than c. What is g of 1 in terms of a, b, and c? The first and the last thought that came into my mind is using good old Vieta's formulae. So let x1, x2, and x3 be the roots of cubic polynomial f of x. For a cubic polynomial, the Vieta's formulae appear as the following. x1 plus x2 plus x3 is minus a. x1, x2 plus x1, x3 plus x2, x3 is equal to b. And the product of roots x1, x2, x3 equals minus c. Since g of x has also 3 roots, it must be also a cubic polynomial. And we know that its leading coefficient is 1. So we write that g of x equals x cubed plus a prime x squared plus b prime x plus c prime. The roots of g of x are reciprocal to the roots of f of x, so we can write them as 1 over x1, 1 over x2, and 1 over x3. Again we use the Vieta's formulae. This time we apply them to the polynomial g of x and read from right to left in order to get expressions for the coefficients. So a prime is minus the sum of inverse roots. This can be reduced to a common denominator x1, x2, x3. We get a fraction where the numerator is just the expression for b, and the denominator is minus c. So a prime is just b over c. Next we evaluate b prime. Again the common denominator is x1, x2, x3. And again we get a familiar expression in the numerator. This time it is minus a. So we found that b prime is a over c. For c prime it's really easy. We get c prime equals 1 over c. And we can write the expression for g of x, where the coefficients are expressed in terms of a, b, and c. We are asked to express g of 1 in terms of a, b, and c. To do that, we just replace x with 1, reduce to the common denominator, and come to choice A. That was so far the easiest problem in part 2. The only mystical thing is where the inequality for a, b, and c is used. To me, the order of coefficients doesn't make a difference, as long as c is non-zero. This completes the first block of problems. The remaining 2 problems in this part are geometrical. The drawings were given in the assignment. Here I try to reproduce them with the best possible accuracy. So, go for them. The problem number 15 was taken out of the previous block of problems, but better later than never. So let's get to problem 15. The figure is constructed from 11 line segments. I didn't count, to be honest, but I trust it, each of which has length 2. The area of the pentagon ABCDE can be written as square root of m plus square root of n, where m and n are positive integers. What is m plus n? I feel terribly sorry to spoil such a nice figure, but I have to do it for the sake of clarity. So I wipe out few lines and let f be common point of the lines drawn from vertices a, b, and c inside the pentagon. We have AB equals BC equals CF equals AF. Therefore, quadrilateral ABCF is a rhombus. And we know that the diagonals of rhombus are perpendicular to each other. One of the diagonals is BF. Let's draw another diagonal AC. So AC is perpendicular to BF, and let P be the point where the diagonals meet. So triangle ABP is a right-angled triangle. Since rhombus is also a parallelogram, P is the midpoint of the diagonals. Therefore, AP equals CP, and the length of BP is half the length of BF, so it is 1. Now from the right-angled triangle ABP, we can find the length of AP, which is square root of 3. In fact, there is a faster way to find the lengths of BP and AP, but let's keep it this way. Since AP equals CP, the length of AC is twice the length of AP, and it is 2 times square root of 3. Now we can find the area of triangle ABC as half of AC times BP, and it is equal to square root of 3. In the similar way, it can be found that the length of AD is 2 times square root of 3, and the area of triangle AED is square root of 3. Now the only thing remains for finding the area of the pentagon ABCDE is the area of the triangle ACD. Since AC equals AD, this is an isosceles triangle. Therefore, the altitude AH is also a median. In other words, H is the midpoint of segment CD. Therefore, the length of CH equals half the length of CD equals 1. Now from the right-angle triangle ACH, we can find the length of segment AH. This is the height of triangle ACD. We get square root of 11 as the length of AH. Now we can find the area of triangle ACD, which is half the length of CD times the length of AH. The area is equal to square root of 11. Finally, we can find the area of the pentagon ABCDE as the sum of the areas of triangles ABC, AED, and ACD. We get 2 times square root of 3 plus square root of 11. However, what we really need is the form of square root of m plus square root of n. Therefore, this time we need to move 2 inside the square root. And we get square root of 12 plus square root of 11. Hence, m plus n is 12 plus 11, which is 23. Choice D. And we are moving to the last problem in this video. Problem 17, a tricky one. Let ABCD be an isosceles trapezoid having parallel bases AB and CD with the length of AB more than the length of CD. Line segments from a point inside ABCD to the vertices divide the trapezoid into 4 triangles whose areas are 2, 3, 4, and 5, starting with the triangle with base CD and moving clockwise as shown in the diagram below. What is the ratio of the lengths AB to CD? While reading the conditions for the first time, I didn't pay attention on the word isosceles, but somehow managed to solve the problem. It looks like another redundant condition to me, so I better strike it through for not confusing you and not getting confused myself. Let O be the point from where all the inner segments are drawn. Let's draw the altitude PQ through the point O, so that point P belongs to side AB and point Q belongs to side CD. Let H1 and H2 be the lengths of segments OP and OQ respectively. Then H1 and H2 are the heights of triangles AOB and DOC respectively. Then the area of triangle AOB is half the length of AB times H1. And the area of triangle DOC is half the length of CD times H2. The areas of triangles AOB and DOC are given. They are 4 and 2 respectively. So we can write that the length of AD times H1 is 8, and the length of CD times H2 is 4. Dividing first equation by the second, we get the ratio of lengths AB and CD times the ratio of heights H1 and H2 equals 2. Let x be the ratio of heights H1 over H2. Then the ratio of lengths AB and CD, which is what we need to find, is 2 divided by x. So if we get x, we solve the problem. Let's continue segments OC and OD until they meet base AB at points E and F respectively. The drawing shows that E and F are both inside the base AB. But it could be like that when both points E and F are on the continuation of the base AB. Note that the trapezium ABCD is actually the same, only point O is shifted. Here is another option, when one of the points is inside AB, another is on the continuation. And still the trapezium ABCD is the same. Since all the drawing use the same isosceles trapezium, the disregarded word isosceles doesn't make any difference, so if you put it back, all the alternatives will be still present. And here comes the tricky question. Should we trust the drawing in something that is not explicitly specified in the condition? I would answer no, especially if there are some reasons to question the drawing. Consider, for example, triangles AOB and AOD. Doesn't triangle AOB look bigger to you? However, its area is supposed to be less than the area of triangle AOD. Later we will find another even more convincing reason for not trusting the drawing. However, as the competition, I certainly wouldn't go into these speculations and consider the drawing as is. Firstly, because the time is limited. Secondly, because nobody cares how you got the answer as long as it matches the answer key. Here comes another tricky question. how fair is a multiple choice test in general. But I'll better leave it without an answer and take the drawing as it looks. Due to parallel lines AB and CD, there are two pairs of alternate interior angles. Angle O of E equals angle ODC, and angle OEF equals angle OCD. Therefore, triangles EOF and DOC are similar, and we can equate the ratios. OE to OC equals OF to OD, and equals the ratio of heights H1 to H2 equals X, as H1 is also the height of triangle EOF. The areas of triangles are related as the squares of sizes, so the area of triangle EOF divided by the area of triangle DOC equals square of the ratio H1 to H2, or X squared. Since the area of triangle DOC is 2, the area of triangle EOF is 2x squared. Now we can move the equations for ratios and the area to the top and free some space. Now consider triangles EOB and COB. They have a common altitude drawn from the vertex B, corresponding to the bases OE and OC. Therefore, the areas of the triangles are related as the lengths of the bases. And as it was found before, the ratio of the lengths OE to OC is x. The area of triangle COB is 3. Therefore, the area of triangle EOB is 3x. Now consider triangles AOF and AOD. They have a common altitude drawn from vertex A, corresponding to bases OF and OD. So the ratio of the areas of these triangles equals the ratio of the lengths OF to OD, which is again x. The area of triangle AOD is 5, therefore the area of triangle AOF is 5x. Now we realize that the area of triangle AOB equals the area of triangle AOF plus the area of triangle EOB minus the area of triangle EOF, which is common for triangles AOF and EOB. Substituting the areas of the triangles in the right-hand sides, we get 8x minus 2x squared for the right-hand side, while the left-hand side is the area of triangle AOB, and this is 4. So we come to the equation 8x minus 2x squared is 4, which can be simplified and written as x squared minus 4x plus 2 equals 0. So we solve this equation and get the roots. x1 and 2 are equal to 2 plus minus square root of 2. Both roots are positive and both stay. Now we can find the ratio of the lengths AB to CD as 2 divided by x. Here we need to get rid of the irrationality in the denominator. The result is 2 minus plus square root of 2. And only one of possible values appears in the choices. However, there is another reason that looks to me more convincing. According to the conditions, AB is longer than CD. Therefore, the ratio of lengths must be more than 1, while 2 minus square root of 2 is less than 1. I wonder why choice 2 minus square root of 2 is not present here. It would probably confuse the competitors even more than the redundant condition. But we can certainly say that the ratio of two bases is 2 plus square root of 2, choice B. And so, but hold on. Choosing plus for the ratio of bases means choosing minus for x. Therefore, h1 over h2 is 2 minus square root of 2, which is less than 0.6. This means that h1 is almost half of h2. However, on the drawing, the segment OP looks even longer than the segment OQ, and this can be easily measured. So the drawing is wrong, but that didn't stop us from getting the correct answer, if the answer is correct. If we question the drawing, why should we trust the answer? So let's briefly consider the alternative cases. Let both E and F be on the continuation of AB. It can be easily seen that the areas of triangles EOF, EOB, and AOF remain unaffected, so we can just copy them. The only thing that really changes is the final equation. In this case, EOF is the biggest triangle, And we write that the area of triangle EOF equals the area of triangle EOB plus the area of triangle AOF minus the area of triangle AOB. The area of triangle AOB is 4. All the other areas can be expressed in terms of x. Again, we get an equation for x. After simplification, we get the same equation as previously, and therefore the same roots. Everything else goes to already seen scenario, so we again get 2 plus square root of 2 for the ratio. Now let's assume one of the points, point E for example, is inside AB, another is on the continuation. This time AOF is the biggest triangle, and the equation looks as the following. The area of triangle AOF is equal to the area of triangle AOB plus the area of triangle EOF minus the area of triangle EOB. Again we substitute and simplify and get exactly the same equation with the same roots and the same result. Now we know that the result doesn't depend on the location of points E and F, so the answer is correct, though the drawing could be more precise. I wonder if there is another solution where there is no need to consider several cases. But I believe the solution presented here also allows to finish part 2 on a good note. The only thing remains to say is, guess what? No, that's not what you happen here at the end of an YouTube video. Because I am annoyed with that, I don't want to annoy you. Just wanted to suggest that you should click the link on the next slide for proceeding to part 3.